Welcome to this explainer. Today we're going to explore one of the absolute most elegant mechanical solutions to a devastating engineering problem, the dynamic vibration absorber. We're talking about taking a machine that is literally tearing itself apart with vibration and forcing it to operate with essentially zero amplitude. It is a fantastic blend of physics and mechanical design, and I can't wait to show you how it works.
Here is our roadmap for today. We'll start with the threat of resonance, introduce the dynamic vibration absorber, dive deep into the mathematics of zero, map out the frequency trade-off, and then wrap things up by working through some real-world engineering design examples.
Let's kick things off with Section 1, the threat of resonance.
As engineers, you already know the golden rule of mechanical design. When your machine's excitation frequency perfectly matches the system's natural frequency, you get resonance. And in our world, resonance usually means catastrophic failure. Imagine a massive industrial motor. If it hits that natural frequency, the vibration amplitudes skyrocket. Now, the easiest fix would be to just change the operating speed, right? Just run it faster or slower. But we can't always do that. An engine might need to run at exactly 6,000 RPM to generate the required power. So we have to find a way to manipulate the physical system itself to eliminate that massive vibration.
And that brings us to our structural hero. We introduce an auxiliary spring mass system. Look at the setup here. We take a secondary mass, which we'll call M2, and attach it to our main vibrating machine, M1, using a secondary spring, K2. The entire purpose of adding this extra weight and spring is to actively shift the natural frequencies away from our operating speed and absorb all that destructive kinetic energy.
Moving right along to Section 2, the dynamic vibration absorber. Let's see how the math actually backs this up.
What's really cool here is how we mathematically translate that physical-mechanical system into a solvable set of equations. We aren't just guessing how big of a weight to bolt on to our machine, we are engineering it exactly. By looking at the system and its equations side by side, we see how mass 1 and mass 2 create a coupled system. When we apply Newton's second law, notice how the forces from that secondary spring, K2, link the two masses together. By assuming a harmonic response, we can solve these to get the amplitude equations for both masses. We call the amplitude for the main machine big X1 and the absorber's amplitude big X2.
This brings us to Section 3, the mathematics of zero. This is where the magic really happens.
So our ultimate goal is to figure out exactly how to make the main machine completely stop moving. We want that X1 amplitude to equal absolute zero. Now, if you look at the equation for X1, it's a massive complex fraction. But here is a beautiful mathematical shortcut. To make any fraction equal exactly zero, you literally only have to look at the numerator. The denominator doesn't matter. So to physically stop the main machine from moving, we just take the numerator of the X1 equation, which is K2 minus M2 times omega squared, and we force it to vanish. We set that exact, simple expression equal to zero, completely bypassing the rest of the messy equation.
By forcing that numerator to zero and just moving the terms around, we extract this incredibly elegant tuning equation. Omega squared equals k squared divided by m squared. This proves mathematically that the absorber will completely neutralize the force on the main machine precisely when the absorber's own natural frequency matches the machine's excitation frequency. The secondary mass vibrates violently so the primary mass doesn't have to move at all. It's brilliant.
But on to Section 4, the frequency trade-off. Because let's be real, in engineering, every single solution comes with a cost.
We've fixed the vibration at our specific operating speed, but we absolutely have to map out what happens to the rest of the frequency spectrum. Look closely at this perfect frequency response plot. Notice the dashed line? That represents the single, terrifying resonance peak of the original 1 degree of freedom system. Now compare that to the solid line, which is our newly modified dual mass system.
The trade-off is incredibly clear on this graph. By adding a second mass, we gain this beautiful deep valley of zero amplitude exactly at our operating speed, right where we need it. However, because it's now a 2 degree of freedom system, we've basically split that original peak into two. We now flank our safe valley with two dangerous new resonant frequencies, omega 1 and omega 2. If the machine ever speeds up or slows down through those exact points, the amplitude spikes to infinity. We have to avoid them at all costs.
Section 5. Engineering Design Examples. Theory is great, but application is everything. Let's put some numbers to this and solve some actual mechanical design problems step by step. Imagine you have a heavy 3,000 Newton diesel engine, and it is vibrating violently on its pedestal at 6,000 RPM.
We know the exciting force is 250 newtons. Our mission? Design an absorber to stop the engine from shaking entirely. But there's a strict physical constraint. The new absorber mass itself is only allowed a maximum movement amplitude of 2 millimeters. Otherwise, it'll hit the casing.
Working through the logic conversationally, first things first, let's get out of RPM and convert the engine speed into radians per second, which gives us 628.32 rads per second. Now, because our absorber must generate a force exactly equal and opposite to the exciting force to cancel it out, we use a simple balance equation. Force equals m2 times omega squared times the amplitude, x2. When we plug in our 2 millimeter limit, the math precisely dictates that we need an absorber mass of about 0.317 kilograms and a spring stiffness of roughly 125,000 newtons per meter.
Okay, the absorber is theoretically built and tuned. But remember that frequency trade-off we just talked about? We have a vital safety check to perform. We have to verify exactly where those dangerous new twin peaks have shifted. We do this by calculating the mass ratio, mu, and solving the complex quadratic roots to find our frequency ratios R1 and R2.
Looking at the results, the math worked beautifully. Our new lower resonance omega 1 sits at 618 rads per second, and our upper resonance omega 2 is at 638 rads per second. So, as you can see, our steady operating speed of 628 rads per second is perfectly nestled safely in that zero amplitude valley right between the newly created asymptotes. Let's tackle an even more complex scenario. What if your machine doesn't just sit at one single speed? Here we have a motor generator set vibrating violently 3,000 RPM, but it actually needs to operate anywhere within a massive range of 2,000 to 4,000 RPM. We must design an absorber that pushes the new resonant frequencies entirely outside this huge operational window.
We want to use a cantilever-mounted mass here, but we hit a wall right away. We don't actually know the effective mass of the main motor itself. It's a mystery. So to solve this, we play detective. We attach a temporary 2 kilogram trial mass tuned to the 3,000 RPM problem speed just to reverse engineer the unknown original main mass.
By firing up the machine with our trial mass, we observed that the temporary new resonances happen at 2,500 and 3,500 RPM. Using this real-world test data, we calculate our ratios and work backwards through the frequency equations. And boom, we discover that the main machine actually has an equivalent mass of exactly 14.87 kilograms.
Knowing the true mass of the system, we can ditch the trial mass. Now we size our final permanent absorber to guarantee that the upper resonance spike, omega 2, happens safely past the machine's absolute maximum 4,000 RPM red line.
The math flawlessly dictates the physical reality for us. By using a larger 10.3 kilogram block with a specific cantilever stiffness of over 1 million newtons per meter, we completely shift the danger zone. The upper resonance is pushed way out to nearly 4,500 RPM, giving us a totally safe operating range across that entire 2,000 to 4,000 RPM band.
We have thoroughly mastered the undamped dynamic vibration absorber today, effectively turning dangerous resonance into zero amplitude safety using pure, elegant mathematics. But this leaves us with a critical engineering question. Nothing in reality is completely without friction. So how does introducing inevitable real-world damping alter those perfect, infinite zero-amplitude valleys we just designed? Well, that is a fascinating problem for you to ponder until next time. Thanks for watching.